Students, today let us see an important theorem from the topic Eulerian graphs from the chapter Graph Theory. The question is this: state and prove a necessary and sufficient condition for a graph to be Eulerian. Or equivalently, we can say that prove that a graph is Eulerian if and only if it has no vertices of odd degree. Or equivalently, we can prove that a graph is Eulerian if and only if all vertices are of even degree. First of all, let us see what is an Eulerian graph. A graph with an Euler circuit is called an Eulerian graph. And what is an Euler circuit? A circuit passing through all the edges of the graph exactly once is called an Euler circuit. First of all, let us prove the if part. That is, let me assume the graph is Eulerian and prove that all the vertices are of even degree. Assume that G is Eulerian. And once I say it is Eulerian, it has an Euler circuit. And let me take that circuit as V1, V2, V3, etc., Vi, etc., Vn to V1. Now this circuit is Eulerian, so it has all the edges exactly once. And hence it has all the vertices of the graph. So since all the edges present to exactly once and all the vertices are also present, we can calculate degree of each vertex using this circuit. Now I classify it into two categories. First of all, let us take internal vertices like V2, V3, Vi, etc., Vn. Now each time, for example, V2 if you take, it's an internal vertex. So via the edge V1, V2, a degree 1 is added. Via the edge V2, V3, a degree 1 is added. So each time a vertex is appearing as an internal vertex, degree 1 plus 1, degree 2 is counted. Suppose the edge is appearing k times, the vertex is appearing k times if I take, then the degree of that vertex is 2k. So for each internal vertex degree is 2k, that is even. So for the first category of vertices, all the internal vertices are of even degree. Now let us take the terminal vertex. Terminal vertex is vertex V1 is the terminal vertex. Now it may appear as an internal vertex already. So if it appears as an internal vertex already m times, its degree is 2m as argued earlier. Now the starting edge V1, V2 and ending edge Vn, V1 contributes degree 1 to the vertex V1. So degree 1 plus 1, degree 2 is added for the terminal vertex. So totally the terminal vertex has the degree 2m plus 2, which is also even. So the terminal vertex also has even degree. Altogether internal vertices have even degree, that are already argued. Terminal vertex also have even degree. So totally all the vertices are of even degree. Now only if part. Assume that all the vertices of G are even degree. Now I am going to claim G is Eulerian. Now I take it suppose not. That is, suppose G is not Eulerian. So I have to get a contradiction by the indirect method of proof. So for that I assume G is the minimal non-Eulerian graph. What is the meaning having all vertices even degree? What is the meaning of minimal? Suppose there is a graph which has lesser edges than G and all vertices are of even degree, then G dash must be Eulerian. That is the meaning of the choice of the word minimal. So if I prove the theorem for a minimal non-Eulerian graph, then automatically for graph having more number of edges is also the same can be proved. So I take prove this one using minimal non-Eulerian graph. Now all the vertices are of even degree, so there is a circuit. Now I choose the largest possible circuit in G. so that it has as many edges as possible in the graph. Now what is the meaning of this choice of largest circuit? There is no circuit bigger than C in the graph G. Now I am going to delete the edges of edges of C, not G, edges of C. If I delete from the graph, then I will get a new graph G dash, that is G minus the deleted edges of circuit. So I illustrate with this example. G is this Eulerian graph, not Eulerian, it has all vertices are of even degree. C is the maximum possible circuit. Now I am going to delete the circuit C. So when I delete the circuit C, all vertices of even degree is deleted. So remaining vertices are having even degrees still. So G dash has all vertices are of even degree. Now I recall we have chosen G is the minimal Eulerian graph. If at all there is any graph which is having lesser edges than G and G has all vertices are of even degree, then that graph will be Eulerian. So by that choice, G dash will be Eulerian. So G dash has an Euler circuit C dash. So this is that circuit C dash in the illustration. Now both the vertices have common vertex U. So since G is originally connected, C plus C dash, concatenate these two circuits, we will get a circuit that is bigger than C, which is a contradiction to the choice of C. We have chosen C is the largest circuit in the graph. So for that choice, this is a contradiction. So this contradiction arises due to our false assumption. What we assume? G is non-Eulerian, we have assumed. So that is false. So G must be Eulerian is our claim. So with this the proof is over, and let us see another theorem in the next video. Thank you.